Calculus. Good morning. Good find, Martin. Good find.
I just looked up why it worked, and it happened to pop up.
Yeah. Did you look at that enough to kind of go, I kind of get it, or did you go, whoa, maybe
It's
some of
still
it can?
kind of. That dude is still a nerd. It's still kind of in my head.
I'm actually, I didn't quite make it this morning, but I'm actually working on my own version of that because I was realizing I'm not going to have time to show you guys that. So I thought, if I make my own really clear one, then I can just send it to you guys, and or maybe I'll have it done while we're kind of working in class. Awesome. So you're here and you're on time. Let's get after it. So my intention with this project is really to, not turn you loose to sort of figure Excel out for yourself, but you're going to turn this in, but I kind of want to, just do it with you so that you can kind of understand the concept of it, the beauty of it. It's really a neat idea. So to that end, I want to show you something cool. So let's see, our table actually went down to, was it 2.9? Or was it 3? I can't remember. I think it was just 2.9. So shrink that dude up a little bit so you can see all of it. Get rid of a row up there. That's pretty close. So do you have this set up? And then I'm going to go back because that yellow color is hurting my soul. There we go. I love green. And so what I'd like to show you now is how to fill up this whole table. And I guess I want to show you one thing. Do you recognize that, if you will, this column here is really just kind of the X value. I'm sorry, this row, like we're saying X is 0, X is 0.01, X is 0.02, X is 0.03, and we're just going forever across this shape. Let me pull up the project one more time. I want to do it with you / even for you a little bit, but I want you to walk away kind of saying, oh, okay, that's kind of cool. I see how that works. So the only thing that's ultimately confusing about this is the fact that we're trying to get this to fit in a rectangle instead of just going forever. So I want to make sure that makes sense to you. In other words, what we just did is we stuck 0 and we said is how tall is that line right there? And then we stuck 0.1 in and 0.2 and 0.3. And it's like, how tall is that line? And we're working our way from 0, well, as this picture shows, all the way out to 3. To yesterday's point, it's kind of cool to understand, kind of powerful to understand that the typical deviation. So in the example I gave, just so you'd understand it, we said, okay, babies are born an average of 22 centimeters long. And we said the average deviation from that is 3. And so notice if you went 1, 2, 3 deviations above that, 3 threes above 22 is 31 inches. Now, if your kid's 31 inches or 22 minus 3 threes, what's that take us down to? 18 inches. Why am I brain farting? Yeah, 13 inches, centimeters, 13 centimeters. The number of people on a bell-shaped curve, which is what it would be true for, say, kids that were born, 99.7% of people kind of land between 3 typical deviations above or below. These are just really neat statistical concepts. And so, as I said yesterday, to be inside 2 standard deviations, 95% of people, that's considered to be sort of normal. And of course, if you were close to the high side of that, it'd be like, well, you're approaching not normal. If you're a little on the other outside of that, it's not like you're abnormal. It's just, that's kind of where you start paying attention. Like, wow, your blood pressure is kind of on the high side. Maybe we should watch this. If you're 3 standard deviations above, if you're outside of that, that is really surprising. Like that's, in the case of like blood pressure or, some medical problem, be like, yeah, that's your way out there, man. We gotta do something right now. You're taking medication, get that blood pressure down or whatever. So this is such a practical math. And so all we're really doing here is saying, if I had all of these y values, there's the height when x is 0 in our equation. There, notice it's getting smaller because it's the right side of the graph. And notice it didn't get smaller by much. And it gets a little smaller and 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 a little smaller. Does it make sense if we did Simpson's rule, because we can't take the integral of such a crazy equation? E raised to negative x squared is basically our equation. You can't take the integral of that easily, if not at all. And so if we took these, what is that? Grabbed all of them down here, it says 11. If I grabbed all 11 of those numbers, and notice there's 11 numbers there, which means 10 rectangles. That's why, remember where we said there has to be 10 rectangles to be 11 numbers to make that 1, 4, 2, 4, 2, 4, 2, 4, 1 pattern kind of work out. I could use Simpson's rule then and actually find the area under the curve from 0 to 0.1. Do you see how Simpson's rule is going to work here? And so, well, just to make sure you're understanding that, let's kind of do that right now. Like, did you get this to work yesterday? Did you get this much of it to work? So we said yesterday, why is that? Oh gosh. Yeah, it's a kind of problem with Excel where I can't. So I'm going to do something that might help you a little bit over here. So can you see that equation a little bit better? Just because it's a little bit bigger. If not, let's make it even bigger. So all I did for that particular equation right there was say, hey, I'd like to take that value up there, the x value of 0.01. Notice it's in location D2. That's why there's a D2 over here. And I said, let's plug it into the equation. Well, that equation was pretty ugly, right? 1 divided by the square root of 2 pi times e raised to the negative x squared divided by 2, or negative 0.5x squared. And so I just plugged that in, right? I plugged that in and out popped 0.39828. That's the height. That's a y coordinate. You tracking with that? This is the x and this is the height, or the y value, I guess you could say. I'll just say y value. It's the y value. That's what these rows really mean. And so now let's use Simpson's rule right here. And you notice on my sheet that I gave you, that's kind of what I said here is like row sum. The next title I gave was row sum. And so we're going to use, and I might even say area sum instead of row sum, because it's not like I'm just adding those numbers up. And so the question is, can you do Simpson's rule with these numbers that are sitting right here? I mean, all you're really doing is saying change of x divided by 3. Isn't this Simpson's rule? Change of x divided by 3 times 1 times this number plus 4 times this number plus 2 times this number plus 4 times 2, 4, 2, 4, 2, 4, 1. Can you write a formula for that? Try it. I'm going to give you a second to see if you can, I don't know, kind of do it without me, but then I'm going to do it with you / for you in 60 seconds. Just want to see if you could get started. By the way, to save a little time, aren't you multiplying a whole bunch of those by 4? So rather than saying times 4 each one, could you group all the 4s together? I'm going to do something, I don't know, just to get my brain straight. Aren't all of these the 4s? Every one of those red ones right there is going to get multiplied by 4, isn't it? And then all of these guys are going to get multiplied by, that's not a good color. It doesn't show up very good. Dark green. I don't like that either. Orange, red, I already used red. Light blue, bam, light blue. All of these blue ones are going to be multiplied by 2s. So maybe when I write that out, instead of going 4, 2, 4, 2, 4, 2, maybe I'll just multiply all the red ones by 4 all at once. And look at the sheet that I gave you. Like the right answer is on my sheet. If you did this right, the right answer is 0.03983. Like if you did it right, you should get that same answer. So let's see if that happens.
Hey Doug, I was working on this yesterday and kind of got this far and wondered what is the cumulative sum or whatever next to the area sum.
Yeah, we'll get to that in a second, but it has to do with what if I don't want to go just from 0 to 0.1, but what if I want to go from 0 all the way to 1? If I want to go from 0 all the way to 1, then I'd have to add up a whole bunch of these that were under the area sum. That's kind of the idea, and we'll get there in just a second. I don't know if that's enough to make you kind of go, oh, I see where you're going with that.
I think it's a little bit. Yeah, let me look.
So let's see, isn't this what I'm doing? I'm saying equals plus sign, that's not an equal sign. I'm saying equals cell C2, C3, which I can just click. I can just click C3 or I can type C3. So that's one of those plus 4. And I actually can't remember. Do I have to say times in Excel or can I just say parenthesis? In algebra, would you say parenthesis? I'm pretty sure it has to be times, but I'm going to leave it alone. And then all of these, this cell D3 plus F3 plus H3 plus J3 plus L. All of those are multiplied by 4 plus 2 times all the blue ones. Bam, E3 plus G3 plus I3 plus K3, bam. And then plus 1 times the last one, bam. So notice it said, we found a typo, like it doesn't like that. And notice it even corrected. I don't know if you can see this, but it says 4 times. In other words, it really did want multiplication signs there. So unfortunately, Excel's not math. And so it wants a multiplication sign. When you want to multiply it, you got to say multiply. 4 parentheses does not mean multiply in Excel. So all that is 1 plus 4 times the number plus 2 times the number plus 4. How come I didn't get the right answer? How come I got 11.9?
You forgot to divide it by your number out in front.
Yeah.
I'm blanking on what to call it.
Yeah. Remember how there was a number out front, right? In front of Simpson's rule. What was that formula?
Delta X over 3.
Yeah, that was your rectangle width. In other words, how wide did you decide to make your rectangles? Well, again, notice, do you see it up here? How far did we jump? We went from 0.02 to 0.03. Our change of X is only 0.01 and we have to divide by 3. So, oh yeah, I forgot that. So I can go back out in this and in front, I can say equals change of X, which is 0.01 divided by 3. And again, I want to say nothing here, but I think I have to say times because it didn't like that earlier. And so, bam. Hey, sweet, got the answer, I think. 3983, yeah, got it. Boom. So what this is saying is roughly 4% Under a bell curve, 4% of kids would be from 22 centimeters long to, well, what does 0.1 represent? That's 0.1 standard deviations. Since our standard deviation was 3, 0.1 of those would be 0.3. So it'd be, this is saying 4% of kids you could expect would be born between 22 and 22.3 centimeters long. That's a prediction, a pretty accurate prediction, if you will, for something that's bell-shaped. Now remember, the good thing is, do you ever have to write that formula again? No, just copy it down. So I'm going to give you a second to get that formula working so that you kind of have a sense of what you're doing. And then let's go fill in the, before we do anything else, let's fill in the green table the rest of the way. Again, we don't have any more work to do here. We already did it once, we're done. But I want to show you some cool tricks about how to copy all of those formulas. I mean, that's a pretty ugly formula, right? So how can I copy that all down through the green table? And notice the green table is taking us from 0 to, well, ultimately 2.9. Well, there's 0.1. You add them together, that's 3. This table is going to take us from 0 to 3 standard deviations, but it's all in one rectangle that I can see all at one time. Again, I'm just trying to find the area under a curve, because in the case of a bell-shaped curve, the area under that curve is actually a percentage. The entire area under the bell curve that goes forever is 1. In other words, 100%. And so if you chop it anywhere and you say, one of the things we do in statistics is say, you know, what percent of kids would be between, say, 16 centimeters and 24 centimeters, we can actually come up with a percentage thanks to the bell curve. We can say, let's take the integral from 16 to 24. It's just that, well, we can't take an integral because it's too hard. And so can we use a machine to do it? Can we use Desmos and just type that in? Yep, you can use Desmos and type that in. Or if you don't understand that much math, remember that you guys are smarter than the average person, so they're not that good at all this stuff. So can you give them a table where then they could use the table and still get that answer right? Again, please interrupt. We're going to kind of spread out here. Some of you are natural computer people, and you'll be kind of speeding on ahead. And don't just sit there. Like ask conceptual questions. Like, I don't understand what this is doing. And again, I'm assuming you know nothing about Excel. It's the first time you've ever opened it. And so I'm more than happy to teach you basic stuff, and let's just play around for the day and end up with this working.
Hey, Doug, I'm doing the cumulative sum and I'm realizing I'm off by like 1,000th of a point from yours. Do you mind showing me your equation for the area sum again?
Yeah, no. Can you see that okay? I'm not sure how big you guys
Yeah,
can see.
no, I see it.
So point.
Yeah, that's exactly what I did.
Is Excel rounding your number of digits? Because I have more digits showing and it's 39828.
Yeah. And so mine is, I didn't even control this, but you can control it. Do you know how to do this? If I clicked on this cell over here, and there's 100 ways to do this, but I'm kind of lazy, and like everything you need is right click. But I think right there, those two little arrows, notice it says increase decimal, decrease decimal. I know that'll do it too. But I can right click and go down to, because you can control almost anything about a cell from by going right clicks, format cells. And so I can go in here and say number, here's the number, and I got all these choices. So I'm going to go to number, and I can say, I'd like to round that to 4 decimal places. And then bam, now it's 4 decimal places. So you can control that if you want to. Otherwise, yours is probably just doing whatever yours did. Keep in mind that answer that I now have sitting there, 0.0398, although it shows rounded, the right answer still goes out a bunch more decimal places. Do you understand that? It's still recorded perfectly. That's what's kind of neat about Excel. But it's like, why display so many numbers? So I think 4 is enough. Like, I'm going to round all mine to 4 eventually. So going out the door yesterday, does this make sense to you? What I want this cell to represent is, well, this is going to be the 0.5 row. Does that make sense? So this is 0.50, 0.51, 0.52, 0.53. So I need to plug in 0.53 into this equation over here, right? For D2, does that make sense? I need 0.53 to get plugged in right there. So watch how I do that. This is kind of cool. We're going to improve our table so that we don't have to copy much. I'm going to go into that cell right there now, and I'm going to say, bam, there's my equation. And you have to put an equal sign in front of it. Otherwise, it just displays as text. It just thinks you're typing a message to the aliens or whatever. As soon as you throw an equal sign in front of it, now, of course, it's gone. Why can't I see it? God, this is frustrating. As soon as I throw an equal sign in front of it, and by the way, I just hit equals. If you try to click someplace else, it thinks you want to add that number to the formula. So you got to kind of, there's a little green checkbox over here, but something's wrong with mine. If I go to the end and hit enter, if you go to the end of it and hit enter, then great. But see, notice that's still reading D2. Well, what do I really want this to read? Like, how am I going to get this to read? Well, this is what you want to say. Because of where I am, I really would like to add row. Let's see, where am I? I'm at B8. I'm at row B8. There's the 0.5. And notice it even highlights the box to say which one. And then I want to add to that F2 plus F2. And close the parenthesis because I want both of those added together first before I square them. There, do you agree? I just plugged in 0.53 now. And so if I go to the end of this and hit enter, does that match the table? If you look at the sheet that I gave you, if I look at 0.53, is that the answer? Is that the Y coordinate? 0.34667. I'm going to check that right now. Make this as big as I can. 0.3. Yeah, 3467. So good, it's working. Now the problem is I got a lot of boxes here. I've got 300 boxes, and so I do not want to type this 300 times. Now watch really carefully. This is kind of cool about Excel, and I'm going to teach you something you probably don't know. But did you notice earlier up here, notice this cell reads F2, and so now it reads G2. This cell reads F2, and when I go to that box, you can say copy paste, but that little box in the lower hand corner, if you drag it over, do you notice it now reads G2? In other words, it kind of reads your mind and says, hey, if you're copying this to the right, then you're probably trying to move the whole formula to the right. And that's exactly right. I was trying to do that. So watch what happens if I go down here. If I drag this to the right, would you agree I want this one to plug in 0.5 and 0.04? So if I drag this to the right, does it work? The answer is, well, it dragged it to the right and gave me G2. If I click on this, notice what it did. It dragged it to the right. But do you see how it dragged it to the right over here? I didn't want it to drag to the right over there. I wanted it to stay at 0.5 because now it just moved the formula out into the table. So when I copied it to the right, all the formulas said, oh, he wants to go to the right, move everything to the right. So would you agree I'd like B8 to stay put when I drag it to the right? I'd like it to stay B8. You with me there? Here's a cool trick. If I go up in front of that B and I put a $sign, you'd never know this if somebody didn't teach you. If you put a $sign, that $sign is telling Excel, hey, when you copy this to right, leave the B alone. Watch what happens when I copy it to the right now. If I grab that, so it still says B8 plus F2. Good, that's what I want it to say. But if I drag it to the right, what's the second one say? B8 plus G2. It left it alone. Notice it's now reading the right location. Because see, I have 300 of these. I want to copy this. I want to copy it through all 300 boxes. I want to write this formula one time and have it all 300 places. I don't want 300 formulas. I don't want to work that hard. So I could actually drag this to the right now, and all of those are correct. Second problem, watch this. What happens if I now, because I dragged it across and everything was fine, but what happens if I drag it down? Can you predict what's going to happen if you drag this formula down? Notice right now it's reading 0.5 and 0.3, or 0.5 and 0.03. And when I drag it down, what's it going to read? Because I want to move to the next line. And of course, when I drag it down, don't I want it to move to 0.06 and 0.03? Like that's the two, that's what I want it to read. And so let's see if it does that. What is that reading? Notice it worked when I dragged it down because it moved from B8 to B9 because I didn't have a dollar sign in front of the 9. It moved down. It said, oh, he wants to move down. He wants to move from row 8 to row 9. But notice the top row screwed up, like it moved down. Well, of course it did. How do you keep that top row from moving down? Well, isn't that row 2? So if I go back up to this and I put a dollar sign in front of the 2, then that's saying leave 2 alone. Don't screw 2 up. I'll show you this again in a second, but let's just see if it works. Let's just see if it's working now. So I'm going to color that cell blue because this is my good one. I'm done now. That blue cell is now perfect and I can copy it to all 300 cells and I'm done. But let's just watch and see if it works. So I dragged it down this time. Change the color back to black so I'm not confused. Let's see, what is that formula reading? Ah, yeah, look at that. See how it's reading perfectly? So it's actually plugging in 0.63. So now I can just copy that cell everywhere on the sheet. It doesn't even matter where you build this. So again, it sounds like you guys can see that okay. So again, you don't have to totally take this in. We're doing this together. I'm just showing you a fast way to get 300 Y values. We need 300 Y values here, and we're going to start adding all of the dumb things together.
So Doug, are you saying if you drag that like diagonally, like it'll fill in all those too?
Yeah, fills in everything.
I thought you could only, so it was actually kind of a pain. I filled in, because I knew about the money sign, but I thought it locked like 0. So I'd lock 0 or like B3 in place and drag it across horizontally, but I didn't think I could go diagonally, if that makes sense.
Yeah. So watch what I'm going to do now. So I'm on this cell right now, and so I'm just saying Control C for copy. And now I'm just going to grab, well, let's see, I can't grab the cell it's in because then I'll copy over. I'm just going to grab all these cells right here and say Control V, paste, boom, done. Let's check one of them out. You know, like what is that cell? Do you see that it just worked? Notice how that's reading 1.6 and 0.08. So that's plugged in 1.68 and it has a Y value of 0.09.
Oh, because you locked B and then locked the row too. I see.
Yeah.
Oh, that's awesome.
So I locked the letter on the left and I locked the number on the right. So that way it's always going to stay reading from the same locations. So now I can say copy, Control C. I can go up here and just copy everything. Control V, I can grab all of these and say Control V. I can grab all of these and say Control V, bam. I'm now done. My whole table's filled up. I got 300 Y values now that I can go to town.
It's way easier.
Isn't that cool? I didn't know that for a long time either. So now I'm going to do a couple things just to clean this up while you're thinking about that. Because I can't see it very well, I'm going to grab all of these cells and simultaneously say, make the numbers black so they stand out. I don't like how it's rounded, so I'm going to decrease the decimal to 4 decimal places because it's not so hard to read then. So now it looks like exactly like the table. I'll come back to this in a second, but I just made that entire table. Well, not this table actually, but I just made a huge table. I made this table now. So if I haven't screwed up, then all the numbers in this green table should be matching the same numbers that I just made a second ago. And again, what are those? They're nothing more than y coordinates right now. And so up here I said f of 1.68. Plug 1.68 in. Where am I? Oh, look, 1.6. And then, oh, there's 0.08. Yeah, if I added those two, that'd be 1.68. If I plug that in, I get a y coordinate of 0.0973. Let's check on mine to make sure that happened. 1.68, 0.0973. Bam, got it. Okay, so good. Let me give you a minute. Chime in, ask me questions. The other reason I think this is really cool is this is what algebra looks like in the real world. All there is some nerd that gets paid $100,000 a year, that's you, who makes stuff like this in Excel so that people can just put numbers in boxes and out pops the answer. Like you're the one in charge of the algebra, or in this case of calculus, like you actually have to know calculus. You got a Simpsons rule to create this table because we need areas. So let's see, I'm gonna center this row. Are you type A? You should be type A. I'm gonna center this row. I'm gonna make that red for area. I'm gonna make that whole row red. I'm gonna turn that whole row because I want it to really stand out. I'm gonna make it some other color. Ooh, yeah, I like that one. Gold accent number 4. So that formula up there is Simpson's rule, and it is reading all of the numbers on the left over there. When I copy it down, notice every one of them is in row 3. So it's like C3, D3, F3, E3, G3. When I copy it down, I want those to all update. I want those to go to 4. And so I don't need any dollar signs, just copy it down, drag, and you can say copy paste, but notice when I look at that row now, yeah, that just added up all the areas from 0.1 to, well, 0.2, because you're actually adding 0.1 and 0.1. So this is actually 0.2. Notice it's adding those together. So it's adding everything from 0.1 to 0.2. That's 11 numbers. That's 11 numbers right there. Notice down at the bottom, the count says 11. That's 11 numbers, and it takes an odd number of numbers, which happens when you have an even number of rectangles. We have 10 rectangles there, 11 numbers, and if I Simpsons rule those 11 y values, I actually get a really accurate answer for the area under that curve from 0.1 to 0.2. And so if that's working, bam, done. There's all my area sums. Notice the numbers are really tiny out here, and they're just teeny tiny. Why is that? Well, remember what you're doing is finding the area under the curve way out here to the right. So there's not much area there. Here in the middle, pretty decent sized area. Now, we're almost done actually. So I've got this area sum right here. So looking at this, these cool classic numbers that you see up here, notice if you're within one typical deviation of the mean, again, with our kid, 22 centimeters, we decided the standard deviation or typical deviation was 3. So if you go from 22 up 3 to 25, 22 down 3 to 19, we said, or we're told that 68% of the kids born would be predictable that 68.26% of the kids born would be between 19 and 25 centimeters. So notice if you went from 0 to 1, then notice that'd be half of that, 34.13%. So 34% of kids would be born between 22 and 25 centimeters. That's what this chart is saying. Notice that's exactly what this red 34 says here. Because that red 34 is a cumulative sum, which means it's basically added all of these up. Remember, this number was 0 to 0.1. This number was 0.1 to 0.2. This number was 0.2 to 0.3, 0.3 to 0.4, 0.4 to 0.5, and so on. And so if I added up all these numbers down to, and watch this on my sheet, you don't even have to add them. If I added up all these numbers right here down to 1, do you see what it says right down there in the bottom? Sum 0.3413. I didn't even write a formula to add them. I just grabbed them all. And so it tells you a couple of stats that often people want, like, hey, maybe the person wants the average. I'll just tell it to them down here. Maybe they want to know how many that is. Oh, there's 10 of them right there. Maybe they want to know what those all add up to. That's what I wanted. Notice that says 34.13%. That's where that number came from. That's why in the world of statistics, if you're a doctor, some of you are going into medicine, this is something you need to understand, because this is how you tell people, you got a problem. Like, your numbers are way different than other people's numbers. 95% of people should be between these two numbers, and you're outside of that. So we got to talk about this. And so these are classic numbers for statistics: 68%, 95, and 99.7. And so that 68.26, notice that's from -1 to 1. We just looked from 0 to 1 and we got exactly that, half that number, 34.13, exactly half. That's why I carried these out as accurately as we did. Is notice I stole this graphic online. I just went and typed in statistics or something and found that graphic and just stuck it in here on my Word doc. But it's like, that's something you learn in a stat class. And if you took stats, probably that's ringing a bell for you right now. No pun intended. And so all I need to do then is add these together. I mean, I'd like to write it down. In the end, when you add those together, you're going to get that last row we're trying to get. You should actually have this entire row right here. It should be an exact match to that row. Notice we just did it down to 1.3413. Okay. So how do I actually add stuff? I mean, if I want the answer to show up there, and I'd like that answer to be kind of right here. So how do I actually add that? Well, there's a real easy command. I mean, one is the plus sign, but then you'd have to go N4 plus N5 plus N6 plus N7 plus N8. Sometimes you're adding a lot of numbers, and so that's a lot of plus signs to have to put in there. So that's kind of annoying. So is there some way that we could do this? Yeah, let's go do this. So here, if I say equals sum, that's the shortcut. And I started a parenthesis, so that's a command. And notice it's telling us right here what sum does. Just start typing numbers. Number 1, comma number 2, comma number 3, comma number 4. But there's even a better way to do it. If you have sum started, all you actually have to do, and you have an equal sign, all you have to do is drag on all of those numbers right there. And notice it says N3 colon N12, which is kind of code for add all the numbers between N3 and N12, including N3 and N12. And then close the parenthesis, Bam, there's my answer. So now that sum is permanent. And maybe I'll leave this to you to think about, but you know, if I copy this down, do you understand it's not going to work? If I try to copy it down, I have to start throwing some dollar signs in here, but I think I'll just type this other one. Notice I'm at 1.9, which if I work my way all the way to the right gets me to 2. So this is actually the sum of all of them. I'm just going to type it, equals sum from N2, let's see, no, is that N? No, it's N3. N3 colon all the way down to N22. And it shows you what you just typed. And so is that the numbers you notice? It kind of boxes it all and says, this is what you just said you wanted to add. And I'm looking at it going, yeah, that is exactly right. I didn't even screw up the 22. Notice if you double that, you get 95%. That's where that 95% came from. So this is what percent of people are between 0 and 2 deviations. So that would be a kid who's 22 centimeters, the average size, plus 2 threes. So what is that? 22 plus 2 threes is 28. So that's the percentage of kids that would be born between 22 and 28 centimeters long. It's going to be 47%, 47.8, 48%. So area under a curve is what I'm after here. Let's see. Both of these started at N3. So I'd like N3 to be left alone. So how do I get N3 to be left alone? I think I put a dollar sign in front of the 3 so that when I copy it down, it just stays 3. But I don't want the other one to be, I want the other one to update. In other words, this cell was right next to N12 and I want to add all the way to the cell next to it. And down here, this cell N22 was right next to it. So I don't think I want to mess with N22. I think all I have to do you guys agree with this, is just put a dollar sign in front of N, in front of the 3. And now I should be able to add this down. Let's see if I copy over the top of 47, let's see if it stays 47. Oh, it did. Cool. Now I can copy my formula. I have to rewrite it. So they all start at N3. Now I can just grab them and bam. Notice if you go clear out to 3 standard deviations, that would be the kid who's 22 plus 3 threes, that'd be 31. What percent of kids are between 22 centimeters when they're born and 31 centimeters? 49.9%. Like, not too many kids are taller than that. 49.9. Let's see, that's 0.001. That's 0.1%. There's only 0.1% of kids that are born longer than 31 centimeters. Future NBA players, I guess. So does it make sense as a doctor if you weighed the, measured the kid and they're like 32 centimeters, and the parent was like, are they normal? You'd be like, no, they're not. Only 0.1%, only 0.1% of people that are born, 1 in 1,000 are born taller than 31 centimeters. Whoa. You can now say statistically that that's unusual. And of course, some unusual is good, right? Maybe tall is awesome. Maybe it's hearing. Maybe it's sight. Maybe it's good. Maybe it's not good. That's your job as a doctor to know what's good. In the end, most of what we know about medicine, and you probably haven't had any occasion to look into any of this, and frankly, neither have I. But I mean, if you have a blood panel done, which is like, what chemicals are in your blood, statisticians have basically taken measurements on people. And the simple example is temperature, right? Isn't your temperature supposed to be 98.7? Like, where did that number come from? It came from measuring hundreds of people's temperatures and see what it was. Does it make sense that would produce a bell-shaped curve? And apparently at the center of that bell-shaped curve was 98.7. And so then you say, okay, well, what's normal to deviate from that? Is it 0.1 degrees? Is it like people pretty tight? Is it a tall, steep bell curve? Or is it normal to vary from that by 1 degree, like a kind of a big number? Is it normal to vary by 4 degrees? Like, you also have to know that what's typical to deviate, and you can get that. That's a calculation that you make that I won't show you right now, but you can make that calculation. And now that you know that, you can use this logic to kind of test somebody. Like, I'm on ski patrol. If I take someone's temperature and it's like, oh, it's not 98.7, it's 96. Well, I'm going to have to know what we're talking about here to be able to say, is that 96? Is that just a little low and it's no big deal? Or is it like, sound the alarms? Start the person, start a blanket in the dryer and get it warm, get this person warmed up. This is dangerous. Or is it like, oh no, it's perfectly normal to be, only 2.7 degrees colder than 98.7. And so, no big deal. You see why this is powerful knowledge? You see why, and in the end, this all comes down to area under a curve. And it comes down to area under a curve, that the area of which you can't do using calculus techniques. You can't find the area under this here nasty curve. That's ugly. And so Simpson's rule says, who cares? I don't care. I don't need to find the integral to do this. So that was our cumulative sum. And so really, in a sense, this is the whole purpose of this page, is just to get those numbers right there. Now we can just throw the rest of it away. We could just print this out. So I'm going to color that something awesome. What's awesome? Yeah, that's awesome. I like that. Blue. And I think I'm even going to add a note here just to, so I understand what this is. This is from 0 to 0.1.
Could you show me the formula that you did for the rows past the first row?
In the green over here?
Yeah.
I'm just clicking on a random one. Notice I'm on this cell right here. Yeah, I'm happy to help you diagnose if something's not right. So stare closely at that. You miss one parenthesis, $1 sign, one minus sign, one, anything's not the same, then it's not going to work.
Okay.
Did you find yours, April? Whatever was wrong with it?
No, mine looks pretty much the same.
So are you just double checking, or is something not right?
No, my number is different, but so I think the formula is wrong, but I got it right for the top row.
Oh, interesting. Huh. Notice how hard formulas are when you can't put them mathematically. Like, I had to type it in a row. And so, man, the parentheses are, I look at it now and I just think, how in the world did I ever even get that right? There's like parentheses everywhere. And oh my gosh. And then on top of it, you can't even just type pi. It's got to be an extra set of parentheses after pi. And then e to a power. You can't even write e. That doesn't know what e is. And so you got to use this function called exp, exponential. Wow.
So are we doing anything else with this, or are we just turning it in once we get everything lined up with yours?
Yep. You just turn it in. Just link it to me. You don't have to pretty it up. I'd like you to at least have, the titles on the top of this, but you don't have to present it or explain Simpson's rule or, make a big presentation out of it. I just want to, again, it's because the class is almost over and so forth. I want to chill pill a little bit.
If we're not doing anything else with this, can I ask a question about the homework?
Absolutely.
So when I was finishing up in the couple ones about air, there's a weird air equation that they specify you want you to use. And I don't know if we went over in class and I missed it,
No,
or
we did not.
because I had to watch the video to figure it out.
Yeah, I said at the end of class, because we ran out of time, I said, I am going to leave those in the assignment as opposed to get rid of them, but I'll just leave them in there as extra credit because we didn't have time to talk about them. And so fortunately, there is a video at the bottom of that. April pointed out that there was that video was put earlier too, and it was all screwed up. And actually, I think we fixed that between. But yeah, how to calculate the error, and so there's.
Well, I was actually wondering where the formula came from.
Mm-hmm.
And like, what the heck does 180 have to do with Simpson's rule?
Yeah, exactly. And so it's neat because I'll just kind of say a couple things out loud while the rest of you are kind of working on this, but yeah, it's kind of a strange formula. It basically says if you take the equation that you're working with, for us, that's e to the negative x squared. And if you take that equation and you take its derivative 4 times, in the case of Simpson's rule, you take the derivative of that, you get an answer. You take its derivative, you take its derivative, you take its derivative. You take the derivative of that statement 4 different times, and then you come out with this expression. And then you say, okay, what's the biggest that value could possibly be? Like in our case, we're trying to establish the, let's see here, let me think about this, error sum metals. Yeah, so we went from 0 to 3 ultimately. In our case, we said we want to know the area under this curve from 0 to 3. And our final answer there was 0.4987. And we use Simpson's rule to do it. And so, because we use Simpson's rule, we know it's only an approximation. Remember, we used a ridiculously small change of x, though, only 0.01. That's a really accurate answer. And so these are really accurate. But we actually don't know what the right answer is. And so what's the area under this curve from 0 to 3? And so we know we're off, but it would be kind of cool if you could know how much you're off. And so that formula ultimately says, to your point, Eve, let me see, did I write this down somewhere? If you take the 4, and this isn't your question yet, Eve. I know you asked why, not what is it, because you watched the video on it. But I don't have it memorized, so I gotta go look at it again. I just remember playing with it the other day and kind of be like, oh, okay, that makes sense. It's on page 577 of your book. But if you take that 4th derivative and then you establish what the biggest answer you possibly get is, and maybe I'll play with this a little bit. I don't want to, again, ignore me if you don't want to know, but maybe I'll answer this question for our problem. Let me think about this. I want to write right now, but I'm trying to decide if I should make this go away. I think I am going to for a second anyway. So let's see, our equation was 1 divided by the square root of 2 pi. Notice Desmos is a lot nicer, like fractions, pi, and so forth. And then it's e, we said, raised to the power of negative, that's not raised to, the power of negative 1/2 x squared. So negative 0.5 x squared. Bam. So while we're here, if I say, what is the integral of that from 0 to 1? What's the area under that curve from 0 to 1? It agrees with what your sheet just said, 0.3413, and then, you know, a bunch of little stuff after that. Notice if you go from -5 all the way up to +5, which is kind of off the screen, notice you get about 1. The area under the normal curve is always 100%, which is really cool. No matter what your mean and standard deviation are, it's always 100%. And so that's why when you take just a chunk of it and say, I want to know the area from here to here, that's why it always is giving you a percentage, because that's 100% of the people. All the people sort of fit under that bell curve. All the kids are under there somewhere. And so the area under that curve is ultimately 1. Note, you can see it's approaching 1, right? But it's not 1 yet. And so, fine. The error formula says if you take the derivative, I wonder if it'll do this. I'm going to graph the equation y equals f prime 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 of x. That's awesome. It did do it. I can't believe it. So the formula says if you take the 4th derivative of your equation, and in our case, we're trying to figure this out between 0 and 3. What's the biggest, what's the worst, the largest value you ever get? Well, notice the graph tells me that it's right there. That's the largest value, whether positive or negative. This is a small value, but it's only 1.3. This is, that was x, I'm sorry, 0.74. The y value is 0.74. That's the biggest one right there, 1.197. And so the error formula in the book says your error will be less than this if you take that number we just got, 1.197, multiplied by the range that you're in. For us, we were saying we're from 3 to 0. So our range was 3 to 0. And then to Eve's point, it suddenly says for no apparent reason, like divide by 180. Like, where did that come from? And then finally multiplied by your change of x, which for us was 0.01, raised to the 4th power. Your error is less than that. That's our error. Whoa. Whoa. That's incredible how accurate that is. Do you recognize what that number says? It says move the decimal point 10 places to the left. That's like off by 2 trillionths. I don't even know what that number is. I got to think about it. I have to write it down. 2 trillionths. I mean, our answer down there at the bottom, it was like 0.4997 or whatever it was. Let's go evaluate this. Dunk, dunk, from 0 to 3. This is what exactly the problem we were just doing. The answer that you had on your sheet from 0 to 3 Now that I'm looking at it, I'm thinking that seems like it's off more. That doesn't make sense to me. Because wasn't it 0.4997 or something like that? 0.4. No, I guess that's it. Yeah, that's right. 0.4987. So that 0.4987 is the area under the curve from 0 to 3. And so we're sitting here saying, well, you know, how accurate is it? Well, notice if I expand it out a little bit, notice Excel actually goes pretty far, but notice at some point it's kind of like, I can't go that far. Can you see all the zeros there are like, it's, I can't do it anymore. Like it's not, it's saying you can write more, but I don't know what to do. So no one would ever need to know this, even 4 decimal places. Just saying, hey, this is 49.9% would be plenty close enough. But it's what we just found out is basically that answer right there is within 2, whatever that is, billionths, trillionths, or whatever. That's within 2 billionths of the right answer, thanks to that error calculation. Now, Eve's question was a little worse than that, which is, you know, what? Like, where did that come from? Why would, there's a lot of questions here. Why would the 4th derivative tell me something about, why would I be throwing the 4th derivative in there? I can see why I would look from 3 to 0, but like, why would I be multiplying it? And why would I be raising the error, the rectangle width to the 4th power? And why would I be dividing by 180? Like, what does that actually mean? The short answer to that is, I don't know, off the top of my head. So even your book apparently seems to be saying, I'm not going to tell you. Like there's not a proof. A lot of times in math books, there'll be a proof of something. It's not in there. So that's a fairly advanced, like a, you know, PhD statistics formula, I have a feeling, because they're not presenting it to us. And I haven't looked at it before, so I don't know actually. So I showed you quickly how error works, but ultimately I didn't answer your question, Eve, because I don't know the answer to it, at least off the top of my head. So, and then this is the formula for Simpson's rule, but there's a different error formula that only requires you to take a second derivative for the other rules. You know, we did, what was the other one? Trapezoid rule. The trapezoid rule is the same looking formula, but you're only taking the second derivative. You're dividing by 12 instead of 180, and you're raising this to the 2nd power, not to the 4th power. And so it's a slightly different formula, but that's kind of cool because remember what we're doing is taking the integral of things and we don't know the right answer. Well, we do, right? Because we can cheat. Look, we have the right answer right there. And it actually allows you to know the error when you don't even know the right answer. That's amazing. We know the right answer. So we in a sense, we don't need this formula because there's the right answer right there. Anyway, that's more than you wanted to know, most of you. So it is nice to center it. I mean, if you save this, I'm changing my mind. That's a waste of time. I'm going to get rid of it. I'm not going to grade it down because you didn't make things blue and orange and, you know, all stand out cool and all that stuff. And you may not feel like you understood what we did, you know, well enough to think, why would I save this? Because I don't really understand what we just accomplished. But I think I at least showed you the door. I think at least you have a sense of this. But the funny thing is when you teach statistics, the prerequisite to statistics at our school is Math 95. And so they're actually using this, but they don't know that it sits on calculus. Do you see what I'm saying? you're in a spot. I mean, ideally you took Math 243 before you got here. And so this means more to you than to other people because you actually really do understand what a mean of 22 centimeters and what a standard deviation of 3 centimeters on a kid actually means. You have a better feel for that. And so these percentages are speaking to you a little bit more deeply, but I think I've showed you enough that you at least kind of see, yeah, that's something. And so it's interesting for me to teach this class to Math 243 students, and I obviously can't say anything to them about calculus and so forth. But you know, do they need to learn calculus just to be able to do this stuff? Well, no, we have software. You know, we just use some of it. Like we have software that will tell us the area under curve. We just did it right there. I mean, there's a way to do this in your graphing calculator, so I can show them. There's kind of buttons, well, algebra buttons that people use to kind of pull this stuff off, and then they don't have to know calculus. That's expensive, right? If you're in Math 95 and it's like, oh, sorry, you got to take 111, 112, Calc 1, Calc 2, and then you can take statistics. That's like a, you know, $3,000 decision. So how about you for $100,000 a year makes a table like this for them so that they can just read it off. And interestingly, tables like this are obsolete. Nobody uses tables for anything anymore. I mean, tables were before we had computers. And so I barely even show them this table because the software is kind of inside their calculator and so forth. But as I said, ultimately, this table right here is printed in every book so that you can read it. So, yeah, we're done. You send this to me before. I think I had it due Sunday night again. And then we'll spend our time kind of reviewing for tests next week. And then we'll live happily ever after.
Can I screen share mine and have you take a look at it just to make sure it looks good so I can submit it?
Absolutely.